Okay, so let's take a look at what are exponents and how we use them. So, if we see an expression like a to the power of n, what that means is um, you have n a factors to give you the product a to the n. Another way of saying that is you multiply a by a, and you keep doing that n times. So for example, if you've got 2 to the 4, you would do 2 times 2 times 2 times 2, which happens to be 16. So a little bit of language. A is the base, and n is the exponent or the index. Um, and for now, we're talking about values of n that are positive. But soon we will run into values of n which are negative. So a couple of points about how to work with exponents. A few rules to keep in mind. So let's take a look at what happens when you have a to the n times a to the n. Well, what does a to the m mean? Well, it means you do a times a times a times a, and you do that m times. And then you multiply it with a times a times a times a, and you do that n times. Now, if you count up all of the a's that you're multiplying, the number of times you're multiplying a, um, you've got m times here, n times here, and so you're multiplying them n plus n times. And to make it clear, let's take a look at an example. So you've got 2 to the 3 times 2 to the 4. So 2 to the 3 means you have 2 times 2 times 2. You multiply 2 by itself 3 times. And 2 to the 4 means 2 times 2 times 2 times 2. You multiply 2 by itself 4 times. Now, if you take a look at how many 2's you've got here in this product, so how many 2 factors you've got here, let's count them up. 1, 2, 3, 4, 5, 6, 7. Well, this gives us confidence that the rule that we wrote up here, that a to the m times a to the n is equal to a to the n plus n, you can see from this numerical example that that works out. So 2 to the 3 times 2 to the 4 is in fact 2 to the power of 3 plus 4, which is 2 to the 7, happens to be 128. Now, you could have, of course, written 2 to the 3 as 8, 2 to the 4 as 16, and multiplied them, and you would have gotten 128. But we wanted to illustrate uh, what happens when you have um, a base raised to a exponent multiplied by the same base raised to a different exponent. And what we see is the result is the base raised to the sum of the two exponents. Okay, well, let's take a look at what happens if you have a to the m divided by a to the n. Well, once again, what is a to the m? It is a multiplied by itself m times. So another way of saying it is there are m a factors in the product which is equal to a to the m. And then what's a to the n? Well, it's a multiplied by itself n times. So here we've got in the numerator a multiplied by itself m times, and in the denominator a multiplied by itself n times. And you can see that n of the m a's will cancel out. And you will be left with m minus n a's multiplied um, together. So to clarify that, let's take a look at this example. Here we have 3 to the power of 6 divided by 3 to the power of 4. So what is 3 to the 6? Well, it's 3 multiplied by itself 6 times. And what is 3 to the 4? Well, 3 multiplied by itself 4 times. And as you stare at this, you can see that 4 of the 6 threes in the numerator will cancel out. And you'll be left with just 2 threes. So your result will be 3 to the power of 2. And you can see that that's equal to 3 to the power of 6 minus 4. Again, building confidence in the rule that we wrote up here, that if you have a to the power of m divided by a to the power of n, you get a to the power of m minus n. Now, a couple of things. So, what happens if a is 0? Well, um, then you just have a 0. It's 0 divided by 0. Um, and you know the statement that we make here is not very meaningful. So we say that in order for the statement to be meaningful, a should not be 0. And now in the previous example, m was greater than n, and so the resulting exponent or the index was positive. Now we take a different example. In this case, the exponent in the numerator is less than the exponent in the denominator. So we've got 3 to the 4 divided by 3 to the 6, and you can see that 4 is less than 6. So we've got 3 times 3 times 3 times 3, so 3 multiplied by itself 4 times, divided by 3 multiplied by itself 6 times. And you can see that some of the 4 threes in the numerator will cancel out the 4 threes in the denominator. And here we have a mistake. So let's fix that. This is supposed to be a 4, and this is supposed to be a 6. So we're just following a rule that 3 to the power of 4 divided by 3 to the power of 6 should give us 3 to the power of 4 minus 6. And we can see why that rule works. We've got here 4 threes on top, 6 threes at the bottom in the denominator, and the 4 threes in the numerator will cancel out 4 threes in the denominator, and we'll be left with 2 threes in the denominator. And if we follow the rule, a to the m over a to the n is equal to a to the m minus n, then we see that we've got 3 to the 4 minus 6, which is equal to 3 to the minus 2. And we can see by looking at the expansion of this 3 to the 4 and the expansion of 3 to the 6 that this is also equal to 1 over 3 times 3. And so this gives us a meaning for negative exponents. What we observe is that 3 to the minus 2 is equal to 1 over 3 to the 2. And so we can write a generic rule that a to the minus n is equal to 1 over a to the n. Okay, so then let's go on. A few more rules here. So now what we've got is you've got a to the power of m And that whole thing is then raised to the power of n. But what does that mean? What that means is, if you stare inside the bracket, we have a to the n, and if you write that out, well, that means a times a, m times. And then you multiply that uh, by itself n times because of this n exponent outside the bracket. And then if you um, think about it, what you've got is m times n a factors multiplying together to give you a to the m times n. Um, let's take a look at an example. So you've got 5 to the power of 3, and then the whole thing is raised to the power of 4. So what that gives you is 5 times 5 times 5, that's 5 to the power of 3, and that's what I put inside the bracket, and then that is multiplied by itself 4 times. Now if you stare at this, you can see that you can just open these brackets up, and what you have is 5 multiplied by itself 12 times. And so you can see that the rule we wrote here, a to the m, and then the whole thing raised to the power of n, is equal to a to the power of m times n, is working out. We had 5 to the power of 3, the whole thing raised to the power of 4, and that's equal to 5 raised to the power of 3 times 4. And you've got 5 to the power of 12, which happens to be this big number. Okay, then we have another rule. If you've got a times b to the power of n, that turns out to be equal to a to the n times b to the n. So let's take a look at an example to see that clearly. So you've got 2 times 3 to the power of 4. Okay, what does that mean? Well, it means you've got 2 times 3 multiplying itself 4 times. 1, 2, 3, 4. Well, now you can collect all the 2's together, and you can collect all the 3's together in separate brackets, and you can see that what you've got is 2 to the power of 4 times 3 to the power of 4. And then if you work it out, it happens to be 1296. But the key thing to note here is the rule works. So you've got a to the b to the power of n, 2 times 3 to the power of 4, and that equals a to the n times b to the n. So 2 times 3 to the power of 4 equals 2 to the power of 4 times 3 to the power of 4. Okay, and now we come to this rule where you've got a divided by b, and this fraction is raised to the power of n. And that turns out to be equal to a to the n divided by b to the n. Now here we don't want the b to be 0, because if b becomes 0, then this a divided by 0 becomes undefined. So we need to make sure that the b is not a 0. But let's take a look at an example. So we have 9 divided by 3 to the power of 4. And if you think about it, this 9 divided by 3, that's a 3 raised to the power of 4. So that's just 3 times 3 times 3 times 3. But you can apply the rule. And you can say, okay, 9 divided by 3 raised to the power of 4, according to the rule, should be 9 times 9 times 9 times 9, divided by 3 times 3 times 3 times 3. And you can see that each 9 gets cancelled, gets divided into by a 3 times. And so you have 9 over 3, 9 over 3, 9 over 3, 9 over 3. So you have 9 over 3 4 times, and each 9 over 3 is equal to a 3. And indeed, this expansion of 9 to the 4 divided by 3 to the 4 is equal to 3 times 3 times 3 times 3, which is what you observe. If you first simplify what you have in the bracket, you get the 3 times 3 times 3 times 3, and you see that if you wrote 9 to the 4 divided by 3 to the 4, you'll get the same result. Okay, so now we finish off with an interesting uh, rule, and we have to carefully make a few observations here. So what happens if we take our first rule, which was a to the m times a to the n is equal to a to the m plus n, and we apply it to a to the half times a to the half. So the m is a half and the n is a half. And that's okay. M and n can be equal. And if we apply the rule though, we've got a to the half times a to the half, and that's equal to a to the n plus n. So a to the half plus a half, which is equal to a to the power of 1, which is equal to a. Now, we remember from earlier work that square root of a times square root of a is also equal to a. So we stare at this and we observe that a to the half is actually equal to square root of a. Okay, let's build upon that. So what about a to the 1/3? Um, so if we had a to the 1/3 times a to the 1/3 times a to the 1/3, applying our rule, we would get a to the 1/3 plus 1/3 plus 1/3. And you're adding 1/3 3 times, so you get a to the 1, which is equal to a. And, uh, uh, and so remembering that cube root of a multiplied 3 times gives you a, we observe that a to the 1/3 is equal to cube root of a. And then we surmise that, okay, it seems that a to the 1 over n is the nth root of a. And with this in mind, we write down our final rule, which can be confusing. So let's pay attention, and then we will solidify this with an example. So the nth root of a to the m is equal to, well, a to the m to the power of 1 over n. So whatever's under the square root, that whole thing is raised to the power of 1 over n. And that is simply applying one of our previous rules. The exponents here just multiply, and we get a to the power of m over n. So let's take a look at an example. So here you've got the cube root of 2 to the 9. What does that mean? Well, it means cube root of 2 multiplied by itself 9 times. So 1, 2, 3, 4, 5, 7, 8, 9. Okay. And so what I did here is I rewrote it where we have cube root of 2 times 2 times 2, and I put that in a bracket, which is then multiplied by itself and then multiplied by itself one more time. And you can see that the cube root of 2 multiplied by itself 9 times is simply 2 multiplied by itself 3 times. And so we can write 2 to the 9 raised to the power of 1/3, according to our rule, should be equal to 2 to the power of 9 times 1/3, which is 9 over 3, which is equal to 2 to the 3rd. And application of the rule agrees with what we observe when we write out what's under the cube root sign, which is 2 to the 9, in an expanded form. So we have our definition of the exponent, and um, we have uh, various rules that we need to learn in order to correctly use the exponent and simplify expressions that contain the exponent in them. So I'm just going to go back and repeat the nomenclature here. So if you've got an expression like this, a to the n, a is the base, n is the exponent, also known as the index. Good, so I recommend that you go and review these rules. Now, I just want to clarify that um, this piece we should fix. Um, because if a is 0 here, then both the numerator and the denominator will be 0. So it's not correct to say that the result will be undefined, it'll just be 0. So um, the better way of saying this is that um, um, a should not equal 0, otherwise the expression is just 0. Okay? So, in order for this expression to make sense, um, a should not be 0. That's it. Now, one last thing that we should add, a final um point, is that anything raised to the power of 0, so um, anything uh, raised to the power of 0 is equal to 1. Okay, so this is an important point that we need to also remember. So let's write this down um, in a form that is a mathematical form here. So we just use our Google tools and we say a raised to the power of 0 is equal to 1. Very important rule to remember, last but not the least. Okay, that's it. Review. If you have questions, post questions, and we'll continue working with exponents in the next lesson.